Okay, so we're going to be working with this book, Modeling Techniques in Predictive Analytics. And this book includes code as well as just explanation about data mining and modeling. And okay, so let's begin. So first of all, he discusses what the meaning of the word model is, and I've talked about it in class. Basically, a model is a way of representing some situation which is very complex in a simpler way. In other words, like you take the economy of Japan and you model it with just a few simple equations relating things like the GDP to something else. So that's called a model. It's much simpler than the entire Japanese economy, but it can be useful, and that's the idea of a model. It's not a complete, perfect representation of some situation, but it can be useful. So we're going to develop models, and hopefully they're going to be useful in predicting various events related to businesses. And we call it predictive analytics. It's also called data science, has many different names, so I might use different words at different times. So you can go through this. I'm not going to go through these details. You can read it yourself. Let's take a look at some of these pictures. So he distinguishes between traditional research, data adaptive research, and model dependent research. So we're going to be learning basically about model dependent research, but we're also going to learn about data adaptive, which is basically the method of data mining. So basically traditional research is when you first specify the model. So you think about what are the important characteristics of whatever you're trying to deal with. If it's the Japanese economy, you might think about different things in the Japanese economy that are important. If it's a business, you might think about different things that are important in the business and try to develop some kind of model. And then based on that, then you check your model with data. So first you specify a model. First you dream up your own model, and then you check whether it makes sense by collecting data and seeing if your model is correct or not. Sort of like traditionally what you do in science, right? You sort of figure out what's going on, how things relate, and then after that you check with data. So that's kind of the traditional approach. And the data adaptive approach is when you don't specify the model beforehand. You don't try and figure out how things are related. You don't do what Newton and Einstein did, where they tried to figure out how the physical world works and then they test it based on data. Rather, you just let the data generate some different models, and you don't you're letting the computer do that work for you, basically. And then so that's what the data adaptive that's what the data adaptive approach is. And he says this is the world of machine learning, sometimes called statistical learning or data mining. Data adaptive methods adapt to the available data representing nonlinear relationships and interactions. So when you specify models, usually because it's kind of complicated to think beyond nonlinear, or maybe in others. Yeah, generally we might come up with linear relationships. It's kind of hard to figure out, like, oh, this thing is related to the square of something else. That's not so straightforward, and so we won't generally come up with that kind of model on our own. But the computer or data mining methods could definitely come up with that kind of model or something much more complicated. So it's called nonlinear, and So we're looking for it will find nonlinear relationships and interactions among variables. The data determine the model. Data adaptive methods are data driven. And then there's model dependent research is another approach. Actually, we won't spend that much time on it, but it begins with specification of a model, like the traditional approach, and then uses that model to generate predictions or recommendations, and that's called simulations or mathematical programming. And he says sometimes, of course, we might want to use a combination of models and methods that work best. So he describes a situation where you're a financial analyst and you might want to use a combination, but we won't go into that because you don't really know what some of these terms mean yet. He says, consider numbers of customers entering a grocery store. Those are called, so the units of analysis there, I want to get used to this term, units of analysis. In this book he calls this thing called units of analysis, are the customers, okay? So they're in Glendale, California on Monday. It's one point in time. Ignoring the spatial location of these stores, these are cross-sectional data. Suppose that, so in other words, he's saying maybe we have 10 different stores. We might not consider the location where they are. We're just interested in the number of transactions that are going on and what the transactions are. In that case, it's called cross-sectional data. Suppose we work with one of those stores, looking at numbers of customers entering the store each day of the week for 6 months. This is called time series data. So if you're looking at data over time, so we want to say how many customers entered today, tomorrow, the next day, and so on. That's what's called time series. In other words, one of the variables in that data set is going to be time. Today, tomorrow, the next day, and so on. Then we look at numbers of customers at all the grocery stores in Glendale, so not just one, across 6 months. These are called longitudinal or panel data. So if you're just looking at time and one other variable, he's calling that time series. But if you're looking at time and several other variables, he's calling that longitudinal. Now he says, okay, besides time, let's look at their location, longitude and latitude. Now that's a different word than longitudinal. I mean, it's being used differently than the word longitudinal was. So we have what we call spatial, or well, we have spatial data, but we also have time, so we call it spatiotemporal data. So we can have that kind of data as well. He says that in this book we're going to consider different kinds of data, these many different kinds of data. And he says we're going to use this as kind of our approach. The value of a model lies in the quality of its predictions. So that's not exactly a traditional approach for, if you look at the theory of economics or other sciences, they don't necessarily strictly adhere to this. But in predictive analytics, this is basically, we say, how good is our model? It's how well it predicts. It's not sort of based on how well it reflects the underlying features or underlying theory of what's going on. It's just how well it predicts. So that's the difference. A traditional approach is trying to understand what's going on sort of underneath the hood, so to speak, whereas here we're just saying if it works, we're going to use it. That's all. Now, we probably won't spend too much time on this kind of thing, but he just reviews. He says, from statistics, so this in traditional statistics, we say that we should quantify the uncertainty. How good is our model? Now, we're certainly going to do that, but how good is our model? On the one hand, we have what are called confidence intervals, which we probably won't get into too much. Point estimates with associated standard errors and significance tests. So if you've taken A little bit of statistics. You should have seen that. That is the classical way. On the other hand, we have probability intervals. It's a little different approach, I guess. Prediction intervals, Bayes factors, subjective, perhaps diffuse priors, and posterior probabilities. So we probably won't get into any of this. The path of Bayesian statistics. So Bayesian statistics is a sort of different approach to statistics. Indices like pardon me, the Akaike information criteria or the Bayes information criteria help us to judge one model against another. So we do want to judge one model against another. I don't know if we'll use these, providing a balance between goodness of fit and parsimony. Okay, central to our approach is the test and training regimen. Okay, so we are definitely going to be doing this, and that is, we're going to break our data set. We have a set of data. Suppose we have 10,000 pieces of data, 10,000 records, 10,000 observations, or as he called it before, 10,000 units of analysis. What we're going to do is we're going to take like maybe 80% of our data and build a so-called model. Let the computer build a model with that data, and then we want to test the model that the computer builds. So we need some data to test. So what we have done now is we've only used 80% for building the model. That's called training. And then we can use the other 20%, to test the model that the computer built. And that's what's called the test and training regimen. He says, we partition sample data, so our data, into training and test sets. We build the model on the training set, and like this, and then we evaluate the models here. Now there's another way to do it, which is actually better, which is a three-way partition. So we have this as the complete data set. I don't know, you can't see it very well. We take the complete data set and we build the model using a training set. Then we choose the best model based on the data in the validation set. So we might come up with 15 different or 20 different models here. Now which one should we use? Which one is better? So we look at the validation data set and we say, okay, well, this model did best on the validation data set, but now we want to say, okay, so we're going to choose that model, the model that did best, but then we want to say, well, how good is it actually? And we don't really want to use the results from here. So we just take another part of the data set, which we call the test set, and we test that single model on this test set, and then we say, oh, that's how well this model does. That's the idea of the three-way partition. And sort of logically, it's a better way to do it. There's also something called cross-validation, which is when we, I think we might be doing that. I forget if this book uses that or not, or I might just talk about it. But that's when you divide this into 10 different parts, and then you use, like, for example, over here, you divide it into 10 different parts, and then you use like 9 of the parts for training and 1 of them for testing, and then you switch. Then you choose a different part for testing and the other 9 for training, and you do that. You rotate like so that and then you can average the results of all of them. So that might be a better way to do it, and that's called cross-validation, or he calls it multifold cross-validation. So that's this picture here. So you have here he divides it not into 10 but into 5, and then he uses this one for testing and these 4 for training. Then he uses this one for testing and these 4 for training, and so on. So that's called iteration 1, iteration 2, 3, 4, and 5. So if you want to find out about the bootstrapping methods, you can check here. Look for these papers or books.